Hello student. In previous lecture we have seen that the pairwise independence of the three events. In this video lecture I am going to explain the concept of conditional probability. First we see the concept of conditional probability. For this, consider this sample space. This sample space is corresponding to family having two children. If family having two children, then sample space omega containing the outcomes mm, both children are male. First children is male, second is female. First children is female, second is male, and both children are female. Now on this sample space, the event A is defined. Event A is that both children are males. Then the event A containing the outcome mm only. Okay. Now the probability of event A, which is equal to m by n. M means number of elements belongs to event A divided by total number of elements in the sample space omega. Therefore, probability of event A is equal to 1 by 4. Now, suppose that it is already known that at least one of the children is boy. Then the sample space or the reduced sample space is, and that sample space is denoted by B. This is the B. B is equal to at least one of the children is boy. It is already known that. Okay. Therefore, B containing the outcomes, both children are male. First is male, second is female. First is female, second is male. And this B is called as the reduced sample space. Now, the probability of event A on the reduced sample space B is, which is equal to what? Probability of A is equal to number of elements belongs to event A divided by total number of elements belongs to the event B. That is, in event A there is only one elements, and in the reduced sample space there are three outcomes. Okay. Therefore, probability of event A based on the reduced sample space, which is equal to 1 by 3, and this probability is called as the conditional probability, and the conditional probability is denoted by A given B. Probability of A given B. Here event B is already known. Then what is the probability of event A? This is the B. B is known. Then we have to find out the probability of event A, and this probability of A is equal to 1 by 3. This is the conditional probability of A given B. Now we know that probability of event A is equal to number of elements in event A divided by number of elements in sample space omega, which is equal to n of A upon n of omega. Then probability of A given B, which is equal to number of elements in A intersection B divided by number of elements in B. B is the reduced sample space here. Therefore, probability of A given B is equal to n of A intersection B divided by n of B. That is, total number of elements belongs to the event A intersection B divided by number of elements in the event B. Now this can be written as n of A intersection B divided by n of omega, this whole divided by n of B divided by n of omega. Okay. Then this gives probability of A intersection B upon probability of B. This is the conditional probability of A given B. Here probability of event B is greater than 0. Now we define conditional probability. The first definition is conditional probability of A given B. The conditional probability of A given B is denoted by P of A given B, and which is equal to probability of A intersection B divided by probability of B. Here probability of B is greater than 0. Similarly, we can define conditional probability of B given A, and conditional probability of B given A is denoted by P of B given A. This is the probability of B given A, which is equal to probability of A intersection B upon probability of A. Here probability of A is greater than 0. Means in conditional probability, if one event is known, then we can find out the probability of the other events. Now we see some theorems on conditional probabilities. The theorem on the conditional probability. Theorem is conditional probability satisfies all axioms of unconditional probability. Namely, for event B defined on a sample space omega with probability of event B is greater than 0. The axiom number 1 is 0 less than or equal to probability of A given B is less than or equal to 1 for any A is subset of omega. Means the conditional probability of A given B lies between 0 and 1, and here A is the subset of omega. Second axiom is probability of omega given B is equal to 1, and axiom number 3 is if A and C are disjoint events on omega, then probability of A union C given B is equal to probability of A given B plus probability of C given B. We have to prove this theorem. Now the proof of this theorem is here the axiom number 1. The proof of axiom number is probability of A given B. By using definition of conditional probability, we have probability of A intersection B upon probability of B, and this probability is greater than 0. Since the probability of A intersection B is greater than or equal to 0, and the probability of event B is also greater than or equal to 0, therefore this ratio is again greater than or equal to 0, and conditional probability of A given B is equal to probability of A intersection B upon probability of B. This probability is less than or equal to probability of B upon probability of B, which is less than or equal to 1. Since A intersection B is subset of B, therefore probability of A intersection B is less than or equal to probability of B. Hence the probability of A intersection B is equal to probability of B. Here we can write this one, probability of A intersection B upon probability of B is less than or equal to probability of B upon probability of B, which is less than or equal to 1. Hence we have 0 less than or equal to probability of A given B less than or equal to 1. Hence the axiom number 1 is proved. Now axiom number 2, probability of omega given B, which is equal to probability of omega intersection B upon probability of B, by using definition of conditional probability. Now intersection between omega and event B is equal to B, that is common elements between sample space omega and event B, which is equal to B. Therefore we have probability of B upon probability of B, which is equal to 1. Hence the axiom number 2 is proved. Now axiom number 3, A and C are mutually exclusive events. If A and C are mutually exclusive events, in this case A intersection C is equal to phi, that is empty set, and we know that the probability of empty set is equal to 0. Therefore, probability of A intersection C, which is equal to 0. Now, the probability of A union C given B, which is equal to probability of A union C intersection B upon probability of B, by definition of conditional probability. Now, A union C intersection B, this can be written as probability of A intersection B union B intersection C. Means this event can be written in this way: A intersection B union B intersection C. Now, here we use addition theorem, and using addition theorem, the probability of A intersection B union B intersection C can be written as, here probability of A union C given B, which is equal to probability of A intersection B upon probability of B plus probability of B intersection C upon probability of B, since the events A and C are mutually exclusive. Therefore, the intersection between A, B and C, which is equal to pi, hence we have this one. The probability of A given B upon probability of B, which is equal to probability of A given B, plus probability of C given B, that is probability of B intersection C upon probability of B, which is equal to probability of C given B. Hence, the theorem is proved. Next theorem on conditional probability is, if A, B, C are any three events defined on omega with probability of event B is greater than 0, then probability of A union C given B is equal to probability of A given B plus probability of C given B minus probability of A intersection C given B. Now, proof of this theorem is, recall that A union C intersection B, this is equal to A intersection B union B intersection C. Therefore, probability of A union C given B, which is equal to probability of A union C intersection B upon probability of B, by using definition of conditional probability. Now, this can be written as probability of A intersection B union B intersection C divided by probability of B. Now, here we use addition theorem for probabilities. A intersection B is the one event and B intersection C is the another event. Means we have only two events and we use here addition theorem for two events. By using addition theorem, we have probability of A union C given B is equal to probability of A intersection B plus probability of B intersection C minus probability of A intersection B intersection C, this all divided by probability of B. Now, this can be written as probability of A intersection B upon probability of B plus probability of B intersection C upon probability of B minus probability of A intersection B intersection C upon probability of B. Now, probability of A intersection B upon probability of B, which is the conditional probability of A given B. Therefore, here probability of A given B. This second term is the conditional probability of C given B. We have probability of C given B and minus probability of A intersection B intersection C upon probability of B, which is equal to the conditional probability of A intersection C given B. Hence, the proof of the theorem. Now, the next theorem is, if A and B are two events defined on the sample space omega, then probability of A dash given B is equal to 1 minus probability of A given B. Here probability of event B is greater than 0. Now proof of this theorem is probability of A dash given B is equal to probability of A dash intersection B upon probability of B by using definition of conditional probability. Now probability of A dash intersection B, which is equal to probability of B minus probability of A intersection B upon probability of B. We have probability of A dash given B, which is equal to probability of B upon probability of B minus probability of A intersection B upon probability of B. Then this is equal to 1 minus probability of A given B. Hence the proof of the theorem. Thank you.